Hey guys, how you doing? So welcome back. Today we are going to solve the third problem of January Daily Lead Code Challenge 2021. And as you can see, this is the problem statement. The name of the problem is beautiful arrangement. The problem statement goes like this. Suppose you have n integers from 1 to n. We define a beautiful arrangement as an array that is constructed by these n numbers. So we know that an array has to be formed that can contain number from 1 to n. And if one of them, it is successful if one of them of one of the following conditions is true for the ith position, where I is 1 based, so it's 1 to n, it's 1 based indexing. The number at the ith position is divisible by I, so basically array of I is divisible by I, so basically array of I mod I is equals to 0. And the second condition is I is divisible by the number at ith position, so I mod array of I is 0. So if either of these two conditions is met, and we have to find out how many ways we can arrange the 1 to n number so that these conditions are met. So the total number of ways we have to provide. Given n, which is an integer, return the number of beautiful arrangements that you can construct. So they have given this example which has 1 and 2, and as you can see, 1 and 2 is a legit arrangement, correct arrangement. And if you can change the arrangement to 2 and 1, 2 is also divisible by 1, and here the position is 2, 1 divides 2. So both, there are two ways we can arrange this. So the way of solving this, and you can see the constraints, it's from 1 to 15, so that kind of indicates us that it might be a bit memory intensive or time intensive solution, and that's why we might need to think in a more exhaustive way. So some kind of a backtracking approach might be the solution, because it seems like we have to think about all the solutions here. So let us take a very small example. Let's say given n is 5. Okay, so for n is 5, the obvious arrangement that we can think of is 1 2 3 4 and 5. Okay, this is the obvious arrangement that we can think of. Now let us understand this, that if we want to find out what are all the possible arrangements, beautiful arrangements of this, we need to understand that, let us say that this problem can be denoted as f, and this is the parameter that we are passing in the f. The array is a parameter. Okay, so this is the main problem that we want to solve. So if we know the answer to this, we will know the answer to our problem. Okay, so this is the problem we are trying to solve. Now let us say if somebody tells us the problem, this sub problem or something like, let us say if we know the solution to f of 1 2 3 and 4, can we solve this problem if we know the solution to this one, if somebody tells us the solution to this one? So let us say um, this is the problem that we already have solved, and let's say this has x number of arrangements. So how many ways can we arrange 5 in this? So 5 can either go here or here or here or here or here, right? So basically I have to insert 5 in any of these places. Now to understand this, let us see, let us call this function to be accepting this parameters 1 2 3 4 5 and the size of the array that we are passing. Okay, now how can we remove the number 5? How many ways can we say that given the array of size 4, how can we add another element to that? How many ways are there to add? So we have to find out 5 can be placed in which of the positions. So 5, this number 5 divides or gets divided by which of this position? So 5 gets divided by this one, basically 5 mod 5 is 0. Then 5 1 mod 5 is 0. So basically 5 mod 5 is 0, 5 mod 1 is 0. Our condition is like that, right? So value mod I equals to 0, or I mod value equals to 0, where I is the index, value is the value at that position. Okay, so this was our condition, and based on this condition we are solving. So we can see that 5 can be placed at this position, 5 can be placed at this position. So there are two ways. So there are two ways or two sub problems that we can disintegrate this problem into. So we have a problem such as if 5 gets replaced by this one, if 5 basically if we want to place 5 here, so what are the remaining numbers we have? We have 2, 3, 4 and 5, and the array of size of this array is 4. Similarly, if 5 is placed here, if 5 is trying to get inside in this location, we'll have 1, 2, 3, 4 and an array of size 4. Okay, so now think in a reverse direction. So if we are given this array 2, 3, 4, 5, if you are given this array 2, 3, 4, 5, and if you want to insert a number, basically this time the number 1 is going to get inserted, we can insert it here. For this array, if number 5 gets inserted, we can insert it here, and we can get this array, get this solution in two ways. So this is one way and this is one way. Got it? Now let us see how this problem can keep on continuing. So this time the size is 4, and we have how many ways? See, 2 is able to divide 4. Okay, 2 is able to divide 4. 4 is able to divide 4 itself. So the position, this is the position I, right? This is the position we want to replace, and these are the values. So if 4 mod 2 is equals to 0, and so I'll denote this mod. So this is becoming a bit long to denote. I'll denote it as 4 mod 2. Okay, 4 mod 2 happens, 4 mod 4 works. So these are those combinations that will return 0, and that's why we can replace. So there are two ways we can form. Once we can replace here, so this becomes 3, 4, 5. Okay, and array size is 3. Another combination is we can replace here, so this becomes 2, 3 and 5. Array size is 3. Okay, let us see for this case. I'll change the color, otherwise it becomes confusing. So similarly 4 here, 4 can replace which one? This 2 here and the 4 here, because this number 2 and 4 will same as this one, like very same as this one. The same combination is followed here as so. Okay, so similarly we'll have f of 1, 3, 4. This is the size of the array. We'll pass it as a parameter, and similarly 4, it's getting inserted here. It has 1, 2, 3. Okay, got it? Similarly, let me just shift this part a bit. Okay, now let me just think about the next level. So what will happen in the next level? 3 gets replaced. 3 can replace only this one, so the only solution to this is 4 and 5. Okay, 3 can replace this one, so the only solution to this is 2 and 5. Okay, similarly we have to keep on continuing this problem. I'll not solve all of them, otherwise this video becomes too long, so I'll just keep on continuing for one of this. So 2 can replace this one, so this becomes f of 5 and of size 1. And what is the base condition? So let us see the base condition now. How many ways we can arrange the input if n is 1? If n is 1, the only solution we have is this array, right? So there is only one way, so the answer in that case is 1. So whenever this second parameter is 1, we can simply return 1. We don't need to recurse anymore. Otherwise, we have a recursive condition. So I hope that kind of explains the solution in a much more intuitive manner. And you have understood how we are kind of disintegrating the array. So given an array 1, 2, 3, 4, 5, if we want to replace all the elements that divides, let's say k, and let's say k divides this element. Oh, okay, let's take this. Okay, let's say k divides 3. Then we are taking this element separately and this element separately and merging them. Okay, so it becomes 1, 2, 4, 5. Okay, okay. So oops. So it kind of becomes 1, 2, 4, and 5. This process of separation of this element from the main array is also going to be needed in the code. Now I want you to understand that while in the process, so while we are doing all of this, so let's say we have a solution to this one. Okay, I'll change the color. Let's say we have a solution to this sub problem, and in some problem of the other, there is a repetition. Let's say these two are the same, exactly not the same in this case, but they can be the same, right? When you end up here, when you end up in the base cases, or let's say when you build up from the base case, there can be a repetition. So to handle that repetition, we'll use what is called memoization. Okay, we'll use memoization. This memoization is a term that is very commonly also we call as top-down DP. DP is for dynamic programming. Top-down DP is nothing but as you solve the problem, you cache the values in some memory, so you solve this problem. Let's say this is a problem. Okay, you solve this problem and the solution to this problem you put it in this memory. So the next time you solve a bigger problem and this problem has a subproblem that is same as this one, you don't need to solve it again. You just can look up from here and send the solution here. That is essentially dynamic programming, but there are two ways of DP: bottom up and top down. We'll not talk about bottom up here because that is not the aim of the video, but this is how top down works. So once we go to the code, you'll understand how we code this, but we'll be doing top down DP here or memoization here to optimize our solution, because otherwise our solution will have n factorial time complexity, right? So we will be optimizing that and making it much more better. So that's it for the explanation. Let us jump into the code, and you can take a few time take some time to pause and go through the understanding of this. So that's it. Let's jump to the code now. Yes guys, so as you can see, I am here in the code screen. So I'll be coding this in Python. You can use your own language, maybe be it Java, C++, JavaScript, anything you want. Even people are coding in Go nowadays. That's really cool. And so let us start the coding process. So what we'll do is we'll create the array. So array is a parameter here for us. So the array we need, which is something like within the range of 1 to n plus 1, because n plus 1 is the range here. That is Python. So this will create an array of something like 1, 2, 3, 4 up to n itself, the number n itself. So that's what this is doing, and we are going to use, so this range will return a iterator object. So we can try with a list. I'll later on show why list will not work, because we want to hash this value if we want to convert it to a DP. Later on we'll see how we're going to figure that out. But for now, let's see. Let's write a method called count, so that we can, this will be the sub problem. So this is the sub problem, that this will solve the sub problem for us. So count will take the array that we create on the on line number 3, and the so we told about the parameter we'll be passing. So that parameter is like the size of this array. So the len of the array is I, and if size is 1, so we know what to return, right? We know we can return 1. So this is the base condition. So this is the base condition for us. What if so otherwise we'll be just be enumerating. So basically for all items that we were checking in the explanation, so for 1 2 3 4 we'll just iterate. So we'll do j, and let's say each and every value, what we call that, so each and every uh, number inside the element, each and every number in enumerate this array. So we'll enumerate this array and we'll iterate over that. So if the number mod I is equals to 0, or I mod number equals to 0, so this is nothing but like iterating over the solution. So that why do we need j? Because we want to split the array based on that index. So I'll show you how that works. So we want a solution. Okay, we need a, so whatever the solution is, we need to store it somewhere. So we'll create a variable called answer, and inside answer we'll keep on adding the solution. So we'll count it. So this is a recursive call where we are going to solve it for the remaining. So this is the array split we are doing. So j is the index that we selected, and this is everything till j, before j, and we are going to add the remaining part. So basically array addition j plus 1. So basically array of j got excluded. Okay, so this is the step that indicates array of j got excluded because it already got counted, and whatever the solution is, we are going to return the answer here. So I hope that explains what we are trying to do. Right now let us try to run this code, because this code has a high complexity, but this should, okay, so we are not returning. Okay, so we have to return the answer outside this. So return answer here. Yup, indentation is very important. So 1 second. Okay, we have to call return the array. Okay, that's it. So let us try submitting the solution. So as you can see, this is accepted, but this will have a high time complexity because we are not caching anything, we are not applying DP. So this has a exponential time complexity, right? This has a very high time complexity because we are simply doing recursion, and we are not, saving the, the calls that are happening multiple times. So what we can do, we can basically create a DP table, and that would be a hash map. So that would be a dictionary here. So this is how we create a dictionary in Python. And instead of doing a list, because so what we want, the DP should store the list, this array list, and the solution, that is the answer mapping for that. But list is not hashable because we need something that can be hashed. So instead of list, we would use a tuple here. Tuples are not unmodified, basically things which type of array like things which cannot be modified. So they can be stringified or things like that. Python internally converts them to hashable objects. Okay, so we'll use a tuple here, and we can create break tuples like this, so that's fine. So here what we'll be doing is this DP is the class variable, as you can understand. So we'll use the caching. So top-down recursion, how it works is, if we have seen the solution here, so first of all, before returning the solution, we would save the solution here. If self.dp of answer is equals to answer, not answer, sorry, self.dp of the array, self.dp of the array is the answer. So that we are storing in the dp array, dp map, And to look up from that, if array in self.dp, if we have that in self.dp, then we don't need to calculate anything. Then just return self.dp of array. That's it, right? And if you see, this solution should also work, but this solution will have a much better time complexity. So I can show you the time complexity of the older one. So 1 second. You can see this has 89% runtime, but if I try to submit this one, let us see. Yeah, this is also got this also got accepted. Let us see the time complexity. Let us see the runtime of this. Should be better. Yeah, see, this is 98.28. So this is definitely much better. And the runtime, you can see this is 44 milliseconds, and this one has a runtime of 124 milliseconds. So you can definitely understand that something is happening here by applying dynamic programming, by applying caching, top-down DP memoization, right? So that is the solution, guys. That is the solution for this problem. And I hope you guys understood the how to solve the problem. And thank you so much for watching. I hope you guys are liking the videos. So do please consider liking, sharing, and subscribing the channel and the videos. And I'll be keeping on posting videos daily for the daily challenge of January. And based on the response I get, I'll continue or stop. So do consider liking or sharing or subscribing, commenting below. That would definitely appreciate me a lot. Thank you so much. And till the next time, goodbye. Happy coding.